My apologies for not joking around because I'm just too worn out. I've been doing this all day and I'm old and I have no energy. Anyway, this is the last problem I worked. I forgot, because I'm old, I forgot to put the solution up. Of course, as you know, I always have the solutions up. And then your turn, this is why I'm showing you this, you should be able to do the percent ionization on your own when I provide you with the concentration of an acid. Look up the Ka for this acid. You can actually punch that into Google and probably get the Ka of that acid. So let's do that. Moving on. What if I have a mixture of acids? How in the heck am I going to do this now, right? So I have a 0.3 molar solution of HF and a 0.1 molar solution of hypochlorous acid. So this is two weak acids mixed together, and they each provide hydronium ions. And to make things worse, we have the auto-ionization of water, so it also produces hydronium ions. Each of those does that. But no worries, this is made really, really easy because the magnitude between the Ka's, meaning the amount of hydronium ion produced, is insignificant for the weaker acids here, right? So this is a factor of 10,000. That's the difference. And so we can ignore the concentration. It will have very little, if any, effect on the concentration of the hydronium ion. It's just going to contribute a little bit, and so we can just ignore this information. Nevertheless, you need to be aware so that when I give you a problem like this, you know what to do. So look up the Ka's, and then you can set up an ice table and calculate the pH or the hydronium ion concentration for HF. Well, okay, let's do that over here. I'll switch to the solution just a little bit too fast. So we have HF that's going to split apart into H plus and F minus. And setting up an ice table, as always, we start out with the 0.300 m and 0 and 0 of the products initially. We only have reactants. Then the reactants is going to break apart by a factor of x, and so the products are going to increase by a factor of x. And so we then at equilibrium can write the concentrations 0.3 minus x and then x and x. I have Ka for HF. So Ka, which is 6.8 times 10 to the minus 4. I forgot to superscript that. Looks like, doesn't matter, not important. Ka equals x squared divided by 0.300 minus x. I'm going to assume this is pretty small and this is fairly large, that this goes to 0, and when I solve for x, x is going to be equal to the square root of 6.8 times 10 to the minus 4 times 0.300. If I put that into my calculator, I get 1.4 times 10 to the minus 3, and before I take the negative log of that, I need to check percent ionization. So this divided by 0.300 times 100, okay, that's not right on my face, equals 4.7%, so barely, but we can make that assumption, and then all we have left is the negative log of the hydronium ion concentration, which we just determined because that's equal to x. So that is, this is equal to 1.85. So that is the pH of that. Summary again, I've got your ice table here set up, and here are all the calculations, the way I've worked them out. This time you don't get a turn. Let's look at strong bases. All right, strong bases are easy, just as easy as strong acids. if I give you the concentration of a strong base, you know that the concentration of hydroxide will be equal to the initial concentration of the base, because we do not have an equilibrium. Let's put AQ here just in case. You get potassium ions and hydroxide ions. So the concentration of KOH initial is equal to the hydroxide concentration, which is what we need to calculate the POH or the pH. And so in order to get the pH, I need to get the hydronium ion concentration. So here we do the relationship of Kw equals the hydronium ion concentration times the hydroxide ion concentration. We know what Kw is, so the hydronium ion concentration, which is what we need, equals Kw divided by OH. Kw is 1.00 times 10 to the negative 14. Just in case, this needs to be at 25 degrees Celsius. You can always assume that the temperature doesn't change for these calculations. And divided by 0.225, and then that gives me 4.4 times 10 to the negative 14 m, and if I take the negative log of that, 4.4 times 10 to the minus 14, I get a pH of 13.4, right? 10 to the minus 14. If this was 1.0 times 10 to the minus 14, you would get a pH of 14. So this is very basic, so it's close. 13.4, very, very basic solution. Well, it's a strong base. Everything dissociates, and so there's that, right? Here's the calculation for you, step by step, all worked out. The dissociation shown here very nicely. And so the question becomes, what do we do when we have a weak base? It's actually very similar to acids. Just instead of the Ka, we used a Kb, right? So we have a base that will subtract or abstract a hydrogen from water. So water here acts as an acid and produce hydroxide ions and the conjugate acid here. And we set up the equilibrium constant. It is going to be the concentration of hydroxide times the concentration of the conjugate acid divided by the concentration of the base. It's cleaner down here, of course. I have everything there. This is liquid, so it's not part of it. So that looks an awful lot like the Ka expression. So the calculations are going to be very similar. So now example 16.5 is asking you for the hydroxide ion concentration and the pH of a weak base solution. This solution is 0.1 molar ammonia. They give you the Kb for ammonia, and so you set up the exact same way, except you have ammonia and then you have conjugate acid and base. And so you know this is going to shift by a factor of x, so minus x, and however that shifts, it breaks apart. It doesn't break apart in this case. It takes the hydrogen off the water, and so you have plus x and plus x, and at equilibrium you have 0.100 minus x, x, and x, and so now we plug this into Kb. The equilibrium expression, Kb is 1.76 times 10 to the minus 5, which is going to be equal to x squared divided by 0.100 minus x. I will make the same assumption I did before, that the percent dissociation is less than 5%, and which will make this 0. Solving for x, I get x squared equals 1.76 times 10 to the minus 5, which is the Kb, times the initial concentration of the base, which is 0.1. And if I take the square root of both sides, This is then X, and this is that. So X in this case, which is the hydroxide ion concentration. That's important, especially if I'm going to ask for the pH, because there's one more step to get to the hydroxide ion concentration from the hydronium ion concentration. So we'll do that real quick here. X is equal to 1.33 times 10 to the minus 3. If I do the test, that's less than 3%, so just trust me or double check. And then we have to get, of course, there are a couple of ways to do this. We can just say that the hydroxide, the hydronium ion concentration, H3O plus, is going to be equal to Kw 1.00 times 10 to the minus 14 divided by the hydroxide ion concentration, right? X here is the hydroxide ion concentration, 1.33 times 10 to the minus 3. So the hydronium ion concentration is equal to 7.52, and I highly recommend that you double check all of my math. I have chubby fingers and put all kinds of weird numbers into the calculator. But it's reasonable here, should be small, and then if I take the negative log of 7.52 times 10 to the minus 12, I get a pH of 11.124, which is of course too many sig figs, but it doesn't matter. So the pH will be higher than 7. It makes sense, right? Because we have a weak base, so your pH should be higher than 7, should be basic. Okay, taking another break. And unfortunately, I'm not done yet, right? And so this is all going to be on the exam, so better keep watching. Just keep watching. I promise I'll keep recording, and you'll keep watching. It's a deal.